So today we are taking notes over torque, which was also the title of the lab that you guys completed in class a couple days ago. So you had a torque lab. We have not yet talked about torque, so we're going to talk about torque today and tomorrow. A couple different types of scenarios that we're going to go through with that as well. But in our notes today, we're going to define torque, axis of rotation, lever arm, and radius. And we're going to use a rigid body system model to show forces causing rotation and free body diagrams, and calculate torque when a force is applied to a lever arm. Okay. You do have upcoming deadlines, same ones that we discussed the other day. Your torque lab is due next week on the 5th. That's Tuesday. That is also the deadline for playlist 2. Test corrections and retests are due by Monday of next week. So if you are planning on finishing up those test corrections, or if you're planning on coming in to take a retest, you are very quickly running out of time. And then lab feedback for the torque lab, if you choose to turn in for feedback, is due tomorrow. Okay, so torque. Let's start with the definition. It is a force applied at a radius from the axis of rotation. It's a measure of the force that can cause an object to rotate about an axis. So if you apply some force at some distance away from a pivot point or away from an axis of rotation, that force could cause that object to rotate about that axis. Okay, and that is when you have a force that does that, that can cause rotation like that, that is a torque. So any ideas where you would see this every single day? Okay, doors would be what I was looking for. Yes, there are lots of examples. But doors, every single day you guys apply a force to a door to push it open, okay, or maybe to pull it closed at some distance away from the hinge. Okay, and so that is an example of a torque as well. Every time you open a door, you push or pull on that door at some point that is some distance away from the hinge, the door hinge. And so you are applying a torque to that door. But yes, there are lots of other examples. I heard car, yeah, you have torque in engines as well. We're not going to get into all that, but we're going to stick with more simple examples like a door, or like what you saw in your lab the other day when you had that meter stick balancing on a ring stand and a pen. Okay, so again, here's our definition again. A force applied at a radius from axis of rotation. So if you aren't understanding what those terms are referring to, you could draw a picture like this to label those things. So if this is my axis of rotation, maybe it's my door hinge, okay, or maybe it is the ring stand from our lab the other day, and you apply a force at this position, then the distance between that force and that axis of rotation is called the radius, or you can refer to that also as a lever arm. Okay, and so this is my lever arm in this example, would be right here. The lever arm, if you want a more specific definition for that, is the perpendicular distance a force is applied away from the axis of rotation. Okay, and so again, this is perpendicular to my force, and it is the distance away from my axis of rotation, therefore that is my lever arm. Again, pictures might help with the definitions if you want to jot something that looks like this down on your paper. Okay, so the amount of torque applied is going to depend on a couple of things. It's going to depend upon the magnitude of the force applied, and it's going to depend upon the lever arm or the length of the radius. And you, again, saw that in your lab that you had the relationships between those things. Okay, so it, again, depends on the force and the lever arm. Think about opening a door. How do you push on a door to cause that torque? If you go to open the door, where do you typically push on a door? In the middle of it? Like at the hinge? Yeah, at the other edge, away from the hinge. Typically, you're all the way on the other side. Okay, again, that is this right here, referring to this right here. And again, this is going to be how hard you push that door. And so those are going to be the factors. If you've ever tried to open a door by pushing in the middle of it, or if you push even closer to the hinge, it's pretty difficult. Okay, it requires a lot more force to get that to open because of that length of your lever arm, or where you're pushing on the door. So again, you can think about those things, but you push forward. Okay, when you're opening a door, if you're pushing like this door right here, you would push forward so that the force is perpendicular to that lever arm. If you were to push at an angle, I don't know why you would do that, but if you were trying to open the door and you were pushing like at an angle as you're opening it, okay, yeah, your force required is going to be different, okay, which is what that was. So that's a third factor, would be the angle between the force and the lever arm. Typically, when we're opening a door, we are pushing perpendicular to the surface of the door, or perpendicular to that lever arm. The equation for torque, okay, is torque, and that is a Greek letter tau. It looks kind of like a T, is equal to FR sine theta. So that's your equation. F sine theta finds the component of force that is perpendicular to the lever arm. So when you're looking at a force, if it is applied at an angle, which does happen sometimes, again, when we're opening doors, we don't typically do that, but you could have forces applied at angles to other types of objects, then you would just want the component of the force that is perpendicular to the lever arm. So if it's at an angle, you would have to do some trig, specifically sine theta, in order to determine that component that would be causing the torque. Okay, so FR sine theta, and again, F sine theta is the component that's perpendicular to your lever arm. So if you look here, sine theta is used to determine the component of the force vector. We already talked about that is perpendicular to the lever arm. So in my example here, FB, okay, FB is completely perpendicular to the lever arm, thus the entire force, all of FB, can be used to rotate whatever this object is. If you were to plug in that angle, you'd call that 90 degrees because that's the angle between FB and the lever arm. It's at a right angle, it's perpendicular. And the sine of 90 degrees is, of course, 1, which means that your torque is just F times R. Okay, because F times R times 1 is just F times R. So the entire force is therefore causing a torque on this object. However, if you push at an angle, so here's a different force being applied at some angle, I've labeled theta, and this is FA, and it is at an angle to the lever arm. And so if you have a force applied at an angle, you have to use sine of theta to determine the component. This is the component specifically that we're looking for. Part of this force is horizontal, part of it is vertical. We're looking for this vertical piece because this vertical piece is perpendicular to the lever arm. So if you had this force at an angle, you would need to use sine to get this component, which is why it's built into the equation like this. F sine theta would give you this component of the force, which is the component that's perpendicular to your lever arm. Okay, and so that's where that's coming from in the equation. So if you guys do have questions or calculations where you have a force applied at an angle, you will need to determine the component that is going to be perpendicular to your lever arm, and you have to use trig to do that, or again, if you just go back to this equation, it's already in the equation. All right, so any force can cause a torque unless, okay, there's a couple things that aren't going to cause rotation, and that is if you apply that force at your axis of rotation. If you go and you try to open my door and you push at the door hinge, which on this door over here is all the way to the left of the door, you're not going to open the door. Okay, you can't push at the door hinge. If you do that, you're not going to cause any rotation because you're pushing at the pivot point. Okay, similarly, if you have an angle between the force and the lever arm is 0 or 180 degrees. So if I was like pushing against the edge of the door, so like if this is my door, if I push like this, I'm not going to cause rotation if I'm on the end of the door, if I'm 0 degrees or 180 degrees from that hinge. Okay, again, mathematically, sine of 0 or sine of 180, or sine of theta at either of those angles is going to give you 0. Remember, again, theta here is the angle between the applied force and the lever arm. Sometimes the diagrams that you're given in the questions are actually going to label some other angle, and you need to make sure to figure out what the angle required for the question is. You always want to look at the angle between the force and the lever arm, so make sure that you're looking at the correct one. Okay, so thus far in this course, up until this point, we have defined all of the systems that we deal with as no internal structure systems, and we've drawn like free body diagrams from just a point. That point mass has represented the center of mass of that object, and the structure did not matter. Okay, that is no longer going to be the case whenever we are dealing with things that are rotating. So we can't use that same type of system where we assume all of our mass is at a single point, because now the place where we put the force is going to affect how the object is going to move. So in this type of system, and the type of system we used previously, we only had to take into account the forces acting on the body and the translational motion because we didn't have rotation. Okay, obviously that is no longer the case. This unit is all about rotation. And so for this unit, we now have to use a different type of free body diagram, a different type of system that we're going to define in order to illustrate and understand how these objects are going to respond to these forces or whatnot, how they're going to rotate. And so we're going to use rigid bodies or rigid body systems, and those are rigid bodies have mass that is distributed through a finite volume. That rigid body analysis has to take into account moments of inertia and rotational motion. To simplify, and it says all this up here, think of no internal structure systems as those that just have mass, just a point mass. Whereas a rigid body has both mass and shape, because now those things are going to matter. We already saw that with different shapes when we talked about rotation, and we had different equations for that moment of inertia. And obviously we saw it in our lab where we had our pen moving at different distances away. We saw changes in those forces. And so now that position is going to play a role, and so we need a different type of system in order to analyze that. Okay, so again, when we draw a free body diagram for a rigid body system, which is what you're going to be doing in this unit, forces must be drawn at the point of contact. It now matters. You can't just draw them all from a single point. Now you have to pay attention to where that force is actually acting on that body because it matters. Okay, so for example, Fg, your force of gravity, the weight of the object, always has to be drawn to the center of mass. So wherever the center of mass is for your system, that's where you're going to draw the vector for Fg. Okay, you can't just draw it at a single point now. Applied forces are shown at the point of contact. So your free body diagram, if you were to have drawn one during your lab, if you drew one for every position, you would have had a whole bunch of different free body diagrams at varying positions down the length of that meter stick, but they would need to be drawn at the point of contact. And so your system also isn't going to show up as a dot. You're going to see that rod, or you're going to see that sphere, or whatever it is that you're dealing with. Okay, so again, when we draw that free body diagram, forces must be drawn at the point of contact. They have to be drawn where they're acting. Okay, Fg acts at the center of mass. Applied forces act at the point of contact. Okay, and again, Fg is always at the center of mass, so whatever system you have, it's always going to be drawn from the center. You can't draw it from like the bottom of the sphere. You'd actually draw it from the literal middle of that circle if you were drawing one for something spherical or a disc or whatever. If your center of mass is not at a pivot point, so if your center of mass isn't at the axis of rotation, then Fg can cause a torque. So even that force of gravity can be part of your torque calculations. And it was in your lab if you were to have calculated anything, because Fg was not at your axis of rotation when you were moving that that balance in pen around. All right, so torque is a vector quantity. So whenever we're dealing with torque, we do have to define rotation, and we have to define the direction of that rotation. We'll do so in a similar manner to how we did with our rotational velocity and our angular acceleration, meaning that we're going to label the directions as clockwise or counterclockwise. And we can abbreviate those as CCW for counterclockwise or CW for clockwise. Kind of as a general rule or as a standard, I'll typically call counterclockwise the positive direction and clockwise the negative direction. And so if you're looking at finding a net torque, meaning let's say you have more than one force acting on whatever your body is, your rigid body system, then you will need to take the sum of those forces that are acting in the counterclockwise direction and add the sum of the forces in the clockwise direction, keeping in mind that one of those has to be negative. And again, we're typically going to call clockwise negative. So you're really subtracting the two. So it's similar to how we did net force previously. Whenever we were dealing with translational motion, you'll have some forces that are in the positive and some that are in the negative. If they're opposite directions, you ended up subtracting them. It's the same idea. If they're opposite rotations here, causing opposite rotations, you'll end up subtracting them because you're going to be adding a negative. By the way, the units for torque are Newton meters. Less commonly, you can see joules per radian. I'm not going to use that, but Newton meters is the unit that you will need to use for torque. All right, so let's try an example calculation. This one says a rod with an axis of rotation at the center of mass has a force applied as shown. Okay, and so here's my center of mass. It says that this is also my pivot point, which means that it can't cause a torque. We talked about that in our notes already. Okay, if your center of mass is anywhere other than your pivot point, it can cause a torque, but not when it's at it. And so it says, what is the torque this force applies? So we're looking for the torque that is created by this 20 Newton force that's being applied at an angle to this rod, whatever it is. Maybe it's a meter stick, okay, whatever. Okay, and that rod is able to rotate freely about this point, which happens to be at its center of mass. And so I've given you some information here. I've given you the length or the distance that this force is applied away from that axis of rotation, and I've given you an angle here. And again, our equation for torque is Fr sine theta. So if we look at this diagram, I know that I have a force of 20 newtons. I know that I have a radius, or again, the length of the lever arm or distance from my axis of rotation is 0.02 meters. Okay, and they do give me an angle, but is this theta? No. Okay, some of you are shaking your head. Okay, this angle is not measuring the angle that we need. What we need is the angle between our force and the lever arm, so we actually need the complementary angle to this one. If you were to imagine extending these to make a right triangle, we're looking for this angle down here. Okay, which makes that one, instead of 53 degrees, this angle theta down here is 37 degrees. Okay, so that's what I said, be careful about where the angle is labeled because sometimes they'll do that to you in the question. All right, so now that we have all of those pieces labeled, we can go ahead and substitute them in. And we can take that 20 newtons and multiply it by our lever arm, 0.02, and multiply that by sine of 37 degrees, and that will give us our torque, which happens to be 0.24 Newton meters. And then my direction is counterclockwise. If you can imagine pulling this upward, it would cause a rotation in this direction. And this is a counterclockwise direction, so I've labeled it as CCW. You do need to include a direction. It is a vector. Okay, are there any questions about this calculation? No? Okay. All right, as I said, we're going to continue with more notes on torque tomorrow, but for the rest of the period today, you can either choose to work on your torque lab if you would like, which is due on the 5th, but feedback is due tomorrow, or playlist 2. And then you do have test correction due date coming up and a retest deadline coming up if that applies to you. So go ahead and get to work on one of those things. If you have questions as you're working, please let me know.